So what kind of questions do you come across in chapter 4 about types of reactions? So as we've learned in the material, we learned that there are types of reactions. One is precipitation reactions. Next, oxidation reactions. Oxidation and reduction reactions. Acid-base reactions. So what kind of questions will you come across in this type of reaction related material? For precipitation reaction, very simple question is, given a compound, given an ionic compound, you will be asked to determine if it is soluble or not soluble. Sometimes they use the term insoluble. It's the same. Not soluble or insoluble, same. Right? So, example. Potassium acetate. Potassium acetate. Or they might give a symbol. Okay, soluble or not soluble. Go back and recollect your table. All acetate are soluble. It could be potassium acetate, sodium acetate, lithium acetate, any acetate, because all acetates are soluble. Lead to chloride, soluble or not soluble? If you remember, all chlorides are soluble. When you remember the chloride part of the table, all chlorides are soluble except for silver, mercury and lead. So lead 2, in fact specifically it was given as lead plus 2 in the table for you. So lead 2 chloride, not soluble. All chlorides are soluble, but this was an exception. So this is the simple version. The next level of complexity in this problem is that you might be given two aqueous solutions, any two aqueous solutions. For example, potassium carbonate and nickel chloride. When these two aqueous solutions are mixed, what's going to happen? Will a precipitate form or not? So what do? We immediately think about what happens when potassium ion and carbonate ion come in contact with nickel plus 2 ion and chloride ion. So switch ions. So there is an attraction between positive and negative. So what are the possible product? Potassium chloride and nickel carbonate. Now this is plus 2, this is minus 2, so nickel carbonate. Now potassium chloride soluble, so we write this as aqueous solution, and nickel carbonate or nickel 2 carbonate not soluble, so solid. And so this nickel 2 carbonate will precipitate out. Now what kind of questions can can you be asked on this specific reaction? You might be asked to just write the products. So when you write the entire reaction like this is known as complete ionic equation. Complete ionic equation or double displacement. Double displacement. Or the question might be, will a precipitate form? Yes, there will be a precipitate formation, and the precipitate is nickel 2 carbonate. What is the ionic equation for that? Nickel plus 2 from here, aqueous, reacts with carbonate ion, aqueous from here, to yield nickel carbonate solid. This is your net ionic equation. Now, what are the two ions that are not present in the net ionic equation? Potassium ion and chloride ion. These two are spectator ions. So, a possible question may be, when potassium carbonate reacts with nickel 2 chloride, what are the spectator ions that will be present in the reaction? So, these two are the spectator ions that will be present in the reaction. Now, the next type of reactions are the redox reactions. So, for example, you would be given a reaction that looks like this. Chloride. So there is zinc solid reacting with iron 2 chloride to form zinc 2 chloride and iron solid. Is this a redox reaction? Yes, it's a redox reaction because oxidation number of zinc is 0 here. Oxidation number of iron is plus 2. Oxidation of zinc is plus 2. Oxidation of iron is 0. So iron from plus 2 to 0, zinc from 0 to plus 2. So there is an increase in oxidation number, there is a decrease in oxidation number. What are the possible questions? What are the oxidation numbers? Oxidation numbers. Oxidation numbers. Which is the oxidizing agent? Which species is the oxidizing agent? Which species is the reducing agent? Which species is the reducing agent? So these are the three possible questions. In this particular example, iron is getting reduced from plus 2 to 0. So zinc is the reducing agent. Zinc is getting oxidized from 0 to plus 2. Iron 2 chloride is the oxidizing agent because iron 2 chloride is oxidizing zinc and zinc is reducing iron 2 chloride to iron metal. Now another simple question in this type of reaction could be, there is a compound, say NaClO4, for example. What is the oxidation state or what is the oxidation number of chlorine? We know how to calculate this. For group 1 metals, oxidation state is always +1. So +1. For oxygen, it is -2. This is a neutral compound. So +1 plus chlorine oxidation state, which we don't know, and in this case maybe I should call it X. So +1 plus X plus 4 times -2 for oxygen is equal to 0. It's a neutral compound. So X plus 1 minus 8 is equal to 0. So X is +7. So oxidation number for chlorine in this case is +7. What about another one? K2Cr2O7. What is the oxidation number of chromium? So again, potassium, first group element, but there are 2 of them. So 2 plus 1 plus there are 2 chromiums. So 2x plus 7 times -2 is equal to 0, because remember this is a neutral compound. So charge is 0. So 2 plus 2x minus 14 is equal to 0. So 2x is equal to 2x is equal to +12. Okay, +12. So x will be equal to +6. What does this mean? Oxidation number of 1 chromium, because remember X is chromium. Oxidation number, oxidation state of chromium is +6. The next type of questions are acid-base related questions, the simple ones. First, HNO3, is it a strong acid or a weak acid? So what is this? What is something that we have to memorize? There is a table of strong acids. For your recollection, HCl, hydrochloric acid, HBr, hydrobromic acid, HI, hydroiodic acid, HNO3, nitric acid, and H2SO4, sulfuric acid, and HClO4, perchloric acid. These are all strong acids. Please make sure to memorize strong acids. Okay? Anything else, for the purposes of this class, any other acid that you don't see in this group is a weak acid. So these are all strong acids. Again, strong bases, sodium hydroxide, lithium hydroxide, potassium hydroxide, calcium hydroxide, barium hydroxide. These are all strong bases. For the purpose of this class, remember these as strong bases. Anything else that you see is a weak base. Most commonly known weak base, ammonia. Most commonly known weak base, right? So the first simple type of question, HNO3, strong acid or a weak acid? We know from this group that HNO3 is a strong acid, right? Now, acid stoichiometry question. So acid reacts with base, right? So your question might look like this. There is an HCl solution, unknown concentration. Unknown concentration meaning we do not know its molarity, concentration. Molarity is one type of expression of concentration. So we do not know its molarity. We take 10 milliliters of that hydrochloric acid and titrate it with sodium hydroxide. You titrate it with sodium hydroxide. You use for this titration 12.54 milliliters of sodium hydroxide. What is the molarity of the sodium hydroxide? 0.100 molar sodium hydroxide. So what is the molarity of the acid that you are using? So you have to imagine a burette like this, okay, and you put sodium hydroxide in the burette. You have seen on the burette, you have seen on the bottle for sodium hydroxide that it is 0.1 molar, and that's what it looks like here, 0.1 molar, and you titrate it against 10 milliliters of HCl. As soon as you put in 12.54 milliliters of sodium hydroxide, the solution turns pink, indicating that the reaction is complete. So what is the concentration of HCl that you're using here? HCl plus sodium hydroxide yields water plus sodium chloride. This is a double displacement, H and OH, H2O, Na and Cl, NaCl, double displacement reaction. Okay, so you're using 12.54 milliliters, 0.01254 liters of sodium hydroxide. Molarity of sodium hydroxide is 0.1 molar. So what does that mean? That means that for every 1 liter of sodium hydroxide, there is 0.1 mole of sodium hydroxide. Now from your reaction, you know that it's a 1:1 mole ratio. 1:1 mole ratio. So every 1 mole of sodium hydroxide reacts with 1 mole of HCl. So you used up totally 0.001254 moles of HCl. But we're not required to calculate the moles of HCl. We are required to calculate molarity of HCl. What is molarity? Moles over liter. So we have the moles of HCl. We also know that we are using 10 milliliters of HCl. So how much is 10 milliliters of HCl? 10 milliliters of HCl is equal to 0.01 liters of HCl. Remember, molarity is always calculated as moles over volume, but the volume has to be in liters. So then 0.001254 moles of HCl reacts with 0.01 liter of has a solution volume of 0.01 liter. What is the molarity of this? 0.1254 molar, right? So when 0.001254 moles of HCl has a volume of 0.01 liters, then this is the molarity. Now remember, writing this reaction is very crucial. We know that it's a 1:1 ratio. What if this was a 2:1 ratio? Then you would have to place 2 here and 1 here. What if it was a 1:3 ratio? Then you will be placing a 1 here and a 3 here. So writing this reaction is very crucial in such cases. So as far as acid-base reactions go, you might be asked for identifying a strong, weak acid or a base, or you might be asked a reaction stoichiometry question based on an acid-base reaction. So the crucial thing, one more time, is to remember how to write acid and base reaction.